There is a story we tell ourselves about the cosmos. It is a tale of exquisite balance and extraordinary violence, a narrative spun from mathematics and light. For decades, this account has stood as a monumental achievement of human intellect, a standard model that seemed to capture the universe's grand design from its first fiery moments to its distant, unknowable future. We thought we had the plot figured out, but a deep and troubling paradox has emerged from the silence between galaxies. A fundamental conflict in our measurements of reality itself now casts a profound shadow over our most cherished theories. This disagreement, a quiet war between two different ways of seeing the cosmos, threatens to shatter the very foundations of modern cosmology. The potential outcome is a revolution in thought so complete that it may erase the most mysterious substance we have ever conceived. Our modern origin story begins 13.8 billion years ago. From an infinitely hot, dense point, all of space-time and energy erupted into existence. The early expansion was a maelstrom of unimaginable force, but as the cosmic furnace-cooled structure began to coalesce, gravity, the patient sculptor, gathered filaments of primordial gas into the first stars and infant galaxies. This magnificent framework, known as the lambda-cold dark matter model, has been stunningly successful. It tells us that the familiar matter of planets and suns of you and me makes up a paltry 5% of the cosmic inventory. Another 25% is an invisible ethereal substance called dark matter, whose gravitational presence is the only sign of its existence. The remaining 70%, the vast majority of reality, was thought to be an even stranger entity, a form of repulsive gravity woven into the fabric of space-time itself. This strange force, called dark energy, was proposed to explain a shocking discovery made at the close of the 20th century. Astronomers observed that the expansion of the universe was not slowing down as expected under the pull of gravity. Instead, the growth was accelerating, with galaxies rushing away from each other at ever-increasing speeds. Dark energy became the engine for this runaway expansion, a constant, pervasive push that will define the cosmos's ultimate fate. This entire beautiful edifice rests upon a single, crucial measurement: the speed of that cosmic expansion today. Known as the Hubble constant, this number underpins everything. It is the metronome of the universe, setting the scale, the age, and the destiny of all that is. Determining its precise value has been a holy grail for astronomers for a century, and for the past decade we have been closing in on it with two profoundly different yet astonishingly precise methods. Herein lies the crisis. The two most reliable techniques for measuring the Hubble constant give us two different answers. The disagreement is not small, and the error bars do not overlap. It is as if two master watchmakers using immaculate tools have built two perfect timepieces that simply refuse to tick at the same rate. This is the Hubble tension. One method begins by looking deep into the past, at the faint residual glow of the Big Bang. This light, the cosmic microwave background, is the oldest photograph of existence we will ever possess. It is a baby picture of the cosmos taken when it was just 3,800,000 years old. Imprinted upon this ancient radiation are tiny temperature fluctuations, the primordial seeds from which all future structures, including our own galaxy, would eventually grow. By studying the size and distribution of these subtle patterns with instruments like the Planck satellite, physicists can construct a definitive model of the early universe. This framework is a recipe book for creation, detailing the exact ingredients of dark matter, ordinary matter, and radiation. With this flawless initial blueprint, cosmologists can run the clock forward. They can project how a cosmos with these specific starting conditions should have evolved over 13.8 billion years, predicting exactly how fast it ought to be expanding today. The result from this approach is unambiguous and exquisitely precise. It predicts a Hubble constant of about 67 kilometers per second per megaparsec. This means for every 3.26 million light-years you travel into space, the universe is expanding 67 kilometers per second faster. It is a prediction of immense power born from the echo of creation itself. The other measurement technique starts from the opposite end of time. Instead of looking back to the beginning, it begins here and now, measuring the cosmos around us. This method involves building a cosmic distance ladder, a series of steps that allows us to gauge distances to progressively farther galaxies. The first rung of this ladder relies on special stars called Cepheid variables. These are pulsating stellar beacons whose intrinsic brightness is directly linked to the rhythm of their pulsations. By observing a Cepheid's pulse, astronomers can calculate how bright it truly is. Comparing this absolute luminosity to how dim it appears from Earth reveals its distance, just as you can estimate the distance of a headlight if you know its wattage. Once the distances to nearby galaxies are secured with Cepheids, scientists can then calibrate an even brighter beacon for the next rung of the ladder, type Ia supernovae. These are the spectacular explosions of white dwarf stars, cataclysms so uniform that they serve as standard candles across the cosmos. When one of these stellar detonations is spotted in a distant galaxy, its apparent faintness tells us how far away it resides. By measuring the redshift of that galaxy's light, the degree to which it has been stretched by the expanding space, astronomers can calculate its speed of recession. Plotting distance against velocity for many galaxies reveals the present-day expansion rate. This local measurement, honed over years by teams of dedicated researchers, is just as precise as the early universe prediction. But it gives a startlingly different number. The result from the cosmic distance ladder converges on a value of roughly 73 kilometers per second per megaparsec. The discrepancy is about 9%. It may not sound like much, but in the realm of precision cosmology, it is a chasm. One of our foundational pillars of knowledge, or perhaps both, must be wrong. For years, the scientific community has been locked in a state of suspense. Could there be some subtle, undiscovered error in one of the measurements? Perhaps the physics of Cepheid stars is more complex than we appreciated. Maybe the dust between galaxies is fooling our telescopes in ways we haven't accounted for. Or is it possible that our model of the early cosmos is incomplete? Countless papers have been written, every conceivable systematic error scrutinized, yet the tension remains. This stubborn conflict has forced physicists to consider more radical possibilities. Some have proposed the existence of new exotic particles in the early universe, a dark radiation that would alter the cosmic evolution. Others have suggested that the nature of dark energy itself might not be constant, that its strength could have changed over cosmic time. These are bold ideas patches designed to mend the beautiful but broken lambda CDM model. But now an even more audacious and startlingly simple explanation is gaining traction. It suggests that the tension is not the result of new physics, but of a profound cosmic illusion. This idea proposes that the conflict is real because both measurements are correct. They are just measuring two different things, a local expansion rate and a global average. And the reason they differ is because of where we live. The solution hinges on a challenge to one of the most fundamental assumptions in cosmology. For a century, our models have been built upon the cosmological principle. This is the idea that on sufficiently large scales, the universe is homogeneous and isotropic, meaning it looks roughly the same everywhere and in every direction. It assumes that the matter in the cosmos is distributed like a smooth, even fog. This principle allows us to treat the entire universe as a single uniform entity, making the mathematics of its evolution solvable. The new proposal asks a deceptively simple question: what if this assumption is not quite true? What if the universe is not perfectly smooth? We know it isn't on small scales. There are planets, stars, galaxies, and vast empty spaces between them. But we always assumed this lumpiness would average out over immense distances. The latest thinking suggests it may not. This hypothesis posits that our Milky Way galaxy resides within a vast underdense region of space, an enormous cosmic void, a bubble hundreds of millions of light-years across, that contains significantly less matter, fewer galaxies, less dark matter than the cosmic average. Inside this Hubble bubble, the gravitational pull is weaker. With less matter to hold things back, the local fabric of space-time would naturally expand faster than the denser, more massive universe outside the void. Imagine baking a gigantic loaf of raisin bread. The dough represents space-time, and the raisins are galaxies. If the dough is uniform, every part of the loaf will rise at the same rate. An ant living on any given raisin would see all the other raisins moving away from it with a speed proportional to their distance. This is our standard cosmological model, but now picture a large air pocket forming in the dough, a region with much less flour. The dough inside this pocket would face less resistance and would puff up faster than the rest of the loaf. An ant inside that air pocket would get a skewed perception of the expansion. It would observe its nearest neighbors rushing away at a surprisingly high speed, leading it to calculate a larger local Hubble constant for the bread. Meanwhile, another ant far away, embedded in the denser part of the loaf, would measure the slower, true, average expansion of the entire thing. This is the essence of the cosmic void solution. Our late universe measurement using the cosmic distance ladder of Cepheids and supernovae is inherently local. It samples the expansion within a few billion light-years of us. If we are floating in the middle of a colossal underdense region, this technique would naturally record the faster local expansion rate of about 73. It would be a perfectly accurate measurement of our specific cosmic neighborhood. Conversely, the early universe method derived from the cosmic microwave background is fundamentally global. The primordial light is an echo of the entire cosmos, a snapshot of the average properties of the whole system at its birth. Its prediction of 67 reflects the slower, true, average expansion rate of the universe as a whole. The tension in this view is not a contradiction at all. It is the first direct evidence that the cosmological principle is not the ironclad law we once believed it to be. The implications of this idea are nothing short of breathtaking. If we live in a cosmic void, it forces a complete re-evaluation of the data that led us to believe in dark energy in the first place. The original evidence for an accelerating universe came from observing distant type Ia supernovae. These exploding stars appeared fainter and thus farther away than they should have been in a universe whose expansion was coasting or slowing down. This dimness was interpreted as evidence that the expansion had sped up in the recent past, pushing them farther than expected. But the cosmic void hypothesis offers an alternative interpretation. Matter flows. Galaxies and material are drawn away from the center of voids and accumulate at their edges, forming dense walls and filaments. Living inside a void means there is a net outflow of matter away from us. As we look out at distant supernovae, the light from those explosions is traveling towards us through regions of space that are moving differently than our own. The gravitational effects of these large-scale structures, these walls and voids, could subtly alter the paths and apparent brightness of light from distant supernovae. The calculations are complex, but some models suggest that the outward flow of matter from our void could account for the observed dimming of these standard candles.
This grand, uneven structure replaces the mystery of dark energy.
Without requiring
Our
any
fate,
actual
it
acceleration
suggests,
at all.
is
Suddenly, the phantom force that makes up 70% of reality begins to look like a ghost. Dark energy, the mysterious cosmic accelerator,
Extraordinary
might be an
claims
artifact, a vast
require
cosmic
extraordinary
misinterpretation born from our unknowingly biased vantage
The Hubble
point.
bubble
We
hypothesis
invented
presents a compelling vision of our
repulsive
cosmos.
force to explain
But
an
even the-
observation that might just be a
By mapping the
consequence of
local
our
universe
provincial
in
address
3D,
in a
we
lumpy,
are finally proving the
inhomogeneous
existence
cosmos.
of these
The
massive
grand
cosmic
accelerating narrative of our universe could be an illusion. If this is true, the genuine expansion rate is the slower one, around 67, predicted by the ancient light of the CMB. A universe expanding at this more leisurely pace, when combined with the effects of cosmic structures, may not require a mysterious accelerator. The need for dark energy could simply evaporate. Its existence was inferred to solve a problem that in this new picture may never have existed in the first place. This is a paradigm shift of the highest order. It suggests our universe is not driven by an enigmatic, invisible energy, but is shaped by the far more tangible, if complex, gravitational dance of matter and emptiness. It replaces a cosmic mystery with a cosmic map, suggesting our fate is tied not to a phantom force, but to our location within the grand, uneven tapestry of existence. The most profound puzzle in physics could be solved by simply acknowledging that we don't have a special seat in the cosmic theatre. We just live in the cheap seats where the view is a little distorted. Of course, a claim this extraordinary requires extraordinary evidence. The Hubble bubble hypothesis is not yet proven fact. It is a compelling and elegant explanation, but it must survive the harsh crucible of observational testing. The first challenge is to prove that we actually live in a void of sufficient size and emptiness to account for the entire Hubble tension. Mapping the three-dimensional structure of the universe is a Herculean task, but astronomers are making progress. Surveys of galaxy distributions have in fact hinted that our local environment might be somewhat underdense compared to the average. But definitively measuring the precise profile of this potential void is at the very limit of our current capabilities. Proving its existence with statistical certainty is the primary goal for many researchers now scrutinizing the cosmic map. Furthermore, this hypothesis makes other testable predictions. If the void is real, we should see its signature in other cosmological observations. For example, the distribution of galaxy clusters should look different from our vantage point than from a location in a denser region. New telescopes like the Euclid Space Mission and the Vera-C Rubin Observatory are designed to map the cosmos with unprecedented breadth and depth. They will provide the data needed to either confirm the existence of our cosmic bubble or rule it out entirely. The James Webb Space Telescope also has a critical role to play. By refining our measurements of the local Hubble constant with even greater precision, it can sharpen the tension, making it harder to explain away with subtle errors. If JWST confirms the high value of 73, the pressure to find a radical explanation like the void hypothesis will become almost unbearable. We find ourselves at a genuine crossroads in our quest to understand the universe. For 2 decades, cosmology seemed to be settling into a comfortable, if strange, standard picture. Now that comfort has been shattered. We are faced with 2 exhilarating possibilities. Either we are on the cusp of discovering new fundamental physics, exotic particles, or dynamic forces that will enrich our standard model, or we are in the midst of a Copernican-scale demotion. Just as Copernicus taught us that the Earth is not the center of the solar system, this new idea suggests our entire galactic neighborhood is not representative of the cosmos as a whole. It reminds us that our perspective is limited and that we must be wary of universalizing our local experience. The solution to the Hubble tension might not lie in adding new mysterious ingredients to our theories, but in subtracting one of our deepest assumptions. The story of the universe is still being written. The final chapter on dark energy has not yet been closed. It may yet prove to be real, a genuine force of nature driving the cosmos toward a cold and empty future. Or it may be remembered as a brilliant phantom, a ghost we chased for a generation because we had not yet realized the true complexity and beautiful imperfection of our own cosmic home. Whatever the answer, the search itself reveals the profound heart of the scientific endeavor. It is a process of relentless questioning, of holding our most elegant theories up to the harsh light of data and having the courage to discard them when they fail. This quiet cosmic conflict, born from a disagreement over a single number, has ignited a fire of curiosity that will light our way to a deeper and undoubtedly more wondrous understanding of reality.